One, two, three. Dear students, we are ready to continue our lectures. And now Alexander Korotin tell you much more about optimal transport and generative computer vision models. Please welcome Alexander.
So, hi everyone, let us continue our lecture on modern generative AI approaches based on flow matching, based on bridge matching, diffusion models, and so on. So today we have a second lecture. The lecture will be a direct continuation of the first lecture, which was related to flow matching. And in this lecture, we'll cover, I would say, much more advanced and complex topic, which extends the topic of flow matching. Well, I say that this is the topic of diffusion bridge models, bridge matching, and will primarily focus on domain translation problems, which are a special case of generative modeling problems. In these domain translation problems, usually not flow matching methods are applied, but bridge matching methods, which are extension of flow matching methods. So first of all, let's discuss what is the plan of our lecture. So the first two parts will be a kind of background. So first we will again briefly recall what is diffusion models. So this time we will recall them in a little bit more detail because today we are going to talk about diffusion related stuff and we'll need to understand some basics like stochastic differential equations and so on. Second, we will talk about domain translation problems. What are these problems and how diffusion models are nowadays applied to solve domain translation problems such as image to image super resolution and so on. And then we will go to the main topic of our today's lecture, basically bridge models. What are these diffusion bridges, how they are applied to domain translation, how to train such models, what are there many different variants applied for different types of domain translation problems, paired domain translation problems, unpaired domain translation problems, and so on. So let's begin. Well, as you all know, yes, modern state-of-the-art generative models for images are primarily based on diffusion models. They're able to generate high-quality content by using the theory of stochastic differential equations and so on. And diffusion models are, in fact, one of the two main paradigms which are nowadays popular in the context of generative modeling for images, and they kind of replaced another paradigm which existed before them, which was called generative adversarial networks. So during the previous lecture with you, we discussed how diffusion models are applied to classical generative modeling problems. So the simplest generative modeling problem, which is approached by diffusion models, is the problem of unconditional data generation, which is informally can be stated as a problem of resampling your data set. So basically you have some data points, for example, samples of some images, and you would like to provide a procedure which is capable of producing new samples which are similar to the samples which you have in the trained data set, but at the same time, they are new samples. Yes. So this problem is usually formalized in the following manner. So you have some data set and you assume that this data set are nothing but independent, identically distributed samples from some unknown data distribution P star, and you need to reconstruct this data distribution. So to build a generative model for this distribution, what this means? This means that you need to provide a procedure to sample new points from this data distribution based on the points which you have in your available train data set. And as we discussed in the previous lecture, so diffusion models are one of the paradigms which nowadays are state-of-the-art methods to solve generative modeling problem, the problem of unconditional data generation. So as I told you, this time we work a little bit more with diffusion related stuff. So let me remind you of some basics of stochastic differential equations, because we will need to dive a little bit more deeper in them today than we did in the previous lecture, because previous lecture was primarily about ordinary differential equations, which are much simpler. Yes, and in fact, we did not have to recall a lot of maybe basics, yes, to work with them, to handle with them. Maybe the only concept which we had to recall is the concept of vector fields. So nowadays, we need to recall the concept of diffusion processes in more details. So basically, what is a diffusion process? So diffusion process is some random process which is described by stochastic differential equations. So of course, there are many different ways to make stochastic differential equations to consider, but within the context of generative modeling, and in particular within the context of our lecture, we will consider only particular type of stochastic differential equations of this form. So basically, what is that? This stochastic differential equation says that we have a random process xt, the evolution of which is governed by two things. So the first thing is the drift, basically the speed vector, how our point moves in a space. But this movement is not deterministic in the sense that in this movement, according to this vector field or drift, in other terminology, yes, we also introduce some noise to our movement process. So our trajectories of our random process are actually not deterministic in the sense that they're not just defined by the initial point, but they defined by initial points and some particular random noise which is inputted during this movement along the trajectory. So we consider throughout the lecture, we will consider stochastic differential equations which have the following form. So basically, we allow arbitrary drift function, yes, as we previously considered in ordinary differential equations, but our amount of noise which we input to the trajectory of the stochastic differential equation will be dependent only on time. It will be a function of t, so it will not be dependent on current point at which we are in a particular time moment. So in fact, this all can be generalized to like point dependent noise schedule, but this is more complicated stuff. It's not actually really needed. So we will consider stochastic differential equation of this type. So what does this mean? In fact, this means that to get some particular point of the trajectory of this stochastic differential equation, we need to integrate this stochastic process. So in the integral form, we can write down this stochastic differential equation this way. One particular simplest variant of stochastic process is the Wiener process or the Brownian motion. So basically, it's a Gaussian process which in which like drift is equal to 0 and diffusion coefficient is just some constant value. Yeah, so this is basically example of trajectories which primarily resemble this Wiener process, so the Brownian motion. Yeah, I think you all know about it from standard courses from from just random processes or probability theory. Okay, so one important thing which you should remember from the courses of random processes, in particular stochastic differential equation. So if we have some diffusion process, which is represented in this form. So for this diffusion, one may write down a so-called backward diffusion or diffusion in the reverse time. Roughly speaking, this diffusion, what it shows? It shows the evolution of the point xt in the forward time, when the time flows forward from 0 to some particular time moment t capital. Yeah. The question is how this evolution can be described in the backward time, when the time flows from t capital, some time moment, to 0. And for this, there are so-called famous Kolmogorov equations, which were derived in the middle of the 20th century. And they say that if we would we want to write down the evolution of our point in the backward time, then we can write down so-called backward diffusion equation, which will differ from forward equation in two things. So first, so there is a misprint. So first, the drift coefficient of this diffusion will slightly differ from the forward drift, and we will need to add a so-called score function. I will explain what is that later. Second, the time here should flow backwards. So basically, this misprint here should be a linear process, in which the time flows not the forward, so the diffusion goes not the forward and the Brownian notch, but in the backward time. And why such backward diffusions are important in modern generative modeling? Because these forward and backward relations, these Kolmogorov equations, they essentially lie at the heart of modern generative models based on diffusions. So how modern diffusion models work? They work in the following manner. So suppose that we would like to generate samples from some data distribution, P star. In this, we usually will denote it by P0 because the diffusion terminology. Yes, so how diffusion models typically work? One writes down some particular diffusion process which gradually destroys the information about your data. So basically, it in the mathematical terminology, it means that we write down some diffusion process which is guaranteed to gradually transform your data distribution P0 to some particular easy to sample and known distribution. For example, random noise, normal distribution with some fixed variance like 1 or sigma or whatever. Yes, and then if we want, so basically this is the so-called forward diffusion, which maps the data distribution to normal distribution. And the main idea of diffusion models is to reverse this process of destruction of the information about the data, the process of noising, and to reconstruct the backward diffusion process. Why it is important to reconstruct the backward diffusion process? Because essentially the backward diffusion process is the process which allows data generation. So if we somehow manage to reconstruct this backward diffusion, then we can easily generate new data by just following this backward diffusion equation by starting from some random noise, so samples from some simple distribution, yes, and then simulating the trajectories of this backward diffusion equation. So what is the difference between the backward diffusion equation and the forward diffusion equation, and how in practice this equation is reconstructed? Well, as I already noted, that there are two differences. The first, time in this backward diffusion equation flows backward from t to 0. But the second difference is that some unknown term appears in this backward differential equation. What is this term? Gradient of logarithm of p of x, t, and t. Basically, this is the logarithm of the marginal density of a diffusion process at time moment t. So basically, if we consider these slices at some points, then this gradient of logarithm of pt will be the gradient of logarithm of these densities at each marginal slice at a time t. Of course, it is unknown. So in practice, to learn a diffusion model and to learn a backward diffusion equation, we need to somehow reconstruct or learn this thing with a neural network. And a standard approach to do this is to apply the technique of score matching, which the technique of score matching. So basically, the main idea of score matching is to learn a neural network which approximates this unknown score function. This neural network is typically called the score neural network, and it has the same shape as in the flow matching. So basically, it takes a point and a time moment, and I'll put some vector. So a naive idea to do score matching is just to do some regression on the true score. And this can be done the same kind of, well, theoretically, this should be done the same way as in like flow matching. So we can solve this regression problem to exactly recover this score function. But the problem is that the score function is unknown. The true score function is unknown because, well, if we would have known this, why would do we need to learn it actually? So this is why there are some techniques which are applied, which are called denoising score matching, which allow to constructing certain regression problems like in flow matching when the target for this regression is some conditional distribution and it is actually tractable for many different diffusion processes which are widely used nowadays. And this thing is optimized in a similar manner as in flow matching. So we sample some points, solve some regression problems, sample some points from diffusion process, do some regression, solve some regression problem, optimize it, and in the end we obtain an approximator for our score function, which can be used after training to generate new data during inference. So basically, how this is done. So this slide was in the first presentation as well. We need to simulate the trajectories of our backward diffusion equation. And this is done by standard schemes like Euler discretization. So when we just discretize our time and do some numerical iterative schemes, and in fact, we just approximate our trajectory numerically, and we generate new data. And of course, to accurately generate new data, we need a lot of discretization steps, which is, well, it's time consuming. It's one of the limitations of diffusion models. I have discussed this during previous lecture. But anyway, let us just briefly recall this. Okay, so, but this was about the problem of unconditional data generation. So when we have some data distribution and we would like to build a diffusion model which is capable of generating samples from this one data distribution. But in practice, of course, the most important application of generative models is conditional generation. When we just not say to our generative model, well, create something from this data distribution, but create something which corresponds to my request, for example, to my text prompt or whatever else. So like text to, so how they differ from unconditional models, you might ask, yeah? And we need to recall this actually, because this will be important for our next main part of the presentation. So the main difference from conditional model and from unconditional generative model is essentially that in conditional generative model, what you do is you just learn a family of diffusion processes, of diffusion models. But this family of diffusion models is just indexed one additional parameter. It's like an index. And this parameter is a condition, for example, text or image and so on. So what we do, we assume that for each condition, we have some data distribution for this condition. For example, if our text request is like car, we have a distribution of cars. If our text request is like cat, we have a distribution of cats. And for each of them, we learn their own diffusion which is conditioned on this parameter, like cat or car or dog or whatever, and so on. So for all these diffusions, what is the difference of these all diffusions? Is that for each of them, we have the same noising process, but different denoising process. So we have a family of denoising processes, and in this, each of these denoising processes, we just have additional condition, which says for which of the conditions this denoising process corresponds to. And in fact, the loss function for such training differs just by adding additional expectation of the condition to this loss function in diffusion models. So, okay, why do I recall this? Well, I recall this because later we're going to talk about conditional bridge matching models, which kind of resemble this stuff, but for image-to-image translation problem. Okay, so what is the quick recap? So there are diffusion models, which are based on some forward noisy process. We restore the backward process which denoises. We do this by techniques which are called score matching. To generate new data, we sample we simulate stochastic differential equations, and this stuff is applicable for conditional problems, like conditional text to image and conditional class to image and whatever. Okay, but this was primarily about like standard generative modeling problems, like when we need to generate new data based on some like either unconditional or based on some condition. But there is another class of generative modeling problems which are called domain translation problems. And let us talk about this. What is this? And what is the difference between them and standard generative model? So in fact, if we talk about standard conditional generative standard unconditional generative modeling, what we have? We have one sample of data, and the goal is to reconstruct this data distribution, one data distribution. In domain translation problems, they differ from classical generative modeling problems because we usually have two samples of data, yes? And these samples of data are assumed to be sample of data from one domain and sample of data from another domain. And the goal is to construct a model which will be able to translate data, will transfer or transform data from one domain to the other domain. And there is a great amount of such generative modeling problems. For example, the standard application of these are various image-to-image problems, such as image restoration. For example, image super resolution, image deblurring, image denoising, restoration of artifacts from images, and so on. Style translation problems, modality translation problems, some problems from medicine related to transfer of MRI data, and so on. The question is, well, how to apply generative models to solve such problems? Can it be done? Well, a short answer is yes, but there are some nuances which have to be considered. First of all, these domain translation problems usually have two formulations which are drastically different. So the first formulation is a so-called paired domain translation. When you have, during training of your model, you have available pairs of data from input domain and from target domain. Yeah, so in this case, this is a kind of standard supervised learning problem because your model knows both inputs and outputs, so it knows how to how the output should look like for particular given input. But unfortunately, in practice, this paired setup is not always available because collecting paired data sets is quite challenging. It's maybe costly, and in some cases, it is very, very hard to collect such data. So usually another setup is also considered, which is called unpaired domain translation. Unpaired is when you just have random samples from one domain, random samples from another domain. They may have actually no correspondences, but even in such a hard problem setting, you need to somehow construct a meaningful generative or translation map between these two domains. Well, let's get back to diffusion model and think about, well, can the diffusion models be applied to such problems? Well, let's first talk about conditional paired or supervised domain translation problem. Can diffusion models be applied here? Well, an answer is yes, and the answer is quite obvious. So diffusion models can be straightforwardly applied to paired domain translation problems. How? The same way as they apply to text-to-image problems. So what we do in text-to-image problems? In text-to-image problems, we learn a diffusion model which conditions on text, yes, on some condition, and learns to generate data corresponding to this text from a white noise by reversing the diffusion process. So we can do the same in the paired domain translation problem. So in paired domain translation problem, we have pairs of data, for example, low resolution image and high resolution image. And we can use low resolution image as a condition to train our diffusion model to generate a high resolution image, basically. Yeah. So for example, so this is a very, very easy. This one. This one is a very intuitive explanation. So what we do? So primarily when we talked about text-to-image models, we just conditioned our model on some text and generated image corresponding to this text from white noise. Now we can easily do the following. We can just condition our diffusion model on low resolution image. For example, if we talk about super resolution problem and learn a conditional diffusion model to generate data corresponding to this condition, in this case is high resolution image from white noise. And in fact, it will be exactly the same notation, exactly the same terminology as in conditional text-to-image model. Just the difference is that our condition is different. Now condition is an image, an input low resolution, for example, image, while previously in text-to-image models, we should have conditioned on text or its embedding. So, okay, but this is about paired domain translation. In paired domain translation problems, okay, we can just take our favorite diffusion model, make it conditional, condition it on image, and, well, learn the diffusion model to solve paired domain translation. Easy. But what about unpaired setup? Can we apply diffusion models to the unpaired setting? So a short answer is no. Why? Because, well, to train a conditional diffusion model, we need to have pairs of data, obviously, because train diffusion model, we need, in our loss function, we had like two inputs. In fact, condition and target. In unpaired setting, we have like either input samples or target samples. So we do not have pairs. So conditional diffusion models are not straightforwardly applicable here. Well, there are some ways how to, with many tricks and heuristics to apply them here, but there are much more reasonable approaches which we are going to discuss today, and they're called diffusion bridges. Okay, so now let's go to the main part of our presentation about the diffusion bridge model. Okay, so basically we're going to talk about the diffusion bridge framework, which differs from the classical diffusion model framework. It differs in several aspects. First of all, in standard diffusion models, what they do, they learn a denoising process always. Yeah, so they build the way that they learn to denoise. Yeah, and the framework which we talk about is more general because, in fact, diffusion model, it is kind of standard diffusion model, kind of doomed or forced to always learn a diffusion which ends in some random noise distribution by its construction, because we can easily provide stochastic differential equations which converge to white noise. Yes, the framework which we are going to talk today about, diffusion bridges, it's more general because it allows to learn diffusion processes between arbitrary data distributions. It is not necessary for one of these two distributions to be white noise distribution or normal distribution. Secondly, while diffusion models always by construction learn to denoise, bridge models learn a different type of diffusion. It's a different concept which is called Markovian projection of stochastic processes. And it is much more general than denoising diffusions and all this related stuff. Well, and secondly, in diffusion models, well, depending on particular type of diffusion models, you may have either finite or infinite time horizon. Well, in diffusion bridges, the time horizon where you consider your diffusion is always finite, so it's like from 0 to t by construction, yes? And compared to diffusion models, diffusion bridges, they are applicable both to paired data setting, paired domain translation, and unpaired. And we're going to talk today about how to do it. So basically, this is the list of most related papers from this direction. It's a very recent direction. So in the sense that the first papers in this direction appeared only in 2022, and it is still under development. Okay, first, what we need to understand. So we're going to talk about diffusion bridge models. So obviously, to talk about this, we need to understand what is a diffusion bridge, because it's in the title of diffusion bridge models. And let's try to understand what is that diffusion bridge. It will be very important for our next presentation. So first of all, suppose that you have some diffusion process. It's just the same process as in diffusion model, for example, yeah, which is described by the following stochastic differential equation. And let's say that this process will be denoted by Q capital, and because we'll need some additional notation, and by small q, we will denote the distribution of this stochastic process. For example, Q of xt will denote the marginal distribution at time moment t. Q of its two variables will denote the joint distribution on two time moments this conditional distribution, etc. What is a diffusion bridge? So basically, we have some diffusion process, and diffusion bridge is the same process, but pinned in 2 points. So what does this mean? This means that this is a conditional diffusion process conditioned on its start and end points. So basically, it is a distribution of the process Q, assuming that it starts and ends at particular given points x0 and xt. Yep. So what is shown here? Here we've shown just some standard linear process, so some its trajectories, how they look like. So what happens if we consider the conditional distribution of this process? If we a priori know that, for example, it starts at one point and x1 and ends at another point. It starts at x0 and ends at some other point, x1, for example. Then it will be a so-called bridge process, which kind of resembles the trajectories of original process, but it is guaranteed to end at a particular point, x1, on which it is conditioned. What is this process? How it can be described in some mathematical maybe terminology? In fact, there is a famous tool from the stochastic differential equations, which is called Dub's H transform, which says that this particular conditional bridge, this conditional process bridge, can be described as a stochastic differential equation as well. So it is kind of the same stochastic differential equation as original process, but its drift is slightly modified. So the drift of this process should be adjusted a little bit by this term, which is the gradient of some conditional transitional distribution of this process from which you consider the bridge. So a short story is, okay, you have some diffusion process. If you want to condition it on particular start and end points, well, you can do it, and you can even write down a stochastic differential equation for it, where everything is usually tractable is if this additional term is tractable. But this additional term is usually tractable for most stochastic differential equations which are considered in generative model. So roughly speaking, bridge process is the original process, but conditioned on two particular start and end points. That's it. Okay, now to move next, we need to know even more complex stuff, which is called reciprocal process. What is a reciprocal process? Well, reciprocal process is quite a complex terminology. In fact, by the word reciprocal in stochastic differential equations, usually a lot more general stuff is meant. But we will talk about a particular class of reciprocal processes which are widely used nowadays in generative bridge models. What is it? So suppose that now let's come back to our domain translation problem. Yeah. First, let's talk maybe about paired domain translation problem. So what we have in paired domain translation problem? In paired domain translation problem, we have some joint distribution on input and endpoints. So basically, we have pairs. Yes. And let's by P of x0, xt denote this distribution of pairs. So what is the reciprocal process? In other words, it's called a mixture of bridges. So basically, it's a stochastic process which is created the following way. So we take, to generate a trajectory of such a process, what we need to do? We need to take start and end points from our distribution of pairs. So from a distribution of P of x0 and x1. So we take some pairs. And then to complete the remaining part of the trajectory, so basically the inner part of the trajectory from 0 to 1, we need to insert the trajectory of some bridge process. So reciprocal process is a process which is built in the following simple manner. So if we want to sample a trajectory, we just sample a pair of start and end points, these trajectories, and then sample a trajectory from the bridge process condition on these particular 2 points. Well, why this process is important? This process, in fact, is the process which later will allow us to construct a diffusion process, which is capable of performing domain translation, data transfer from one distribution to the other. But in the current form, this process was denoted by R, which constructed this kind of useless because it's not useful for generative modeling at all. So what we need to do in generative modeling? In generative modeling, we need to take as input point x0 and generate some point x1, yeah, corresponding to this point. By this process, we cannot do this because to build a trajectory of such process, we need to have both input point and end point. Yes, so this is similar to flow matching. Yeah, in flow matching, we constructed some kind of interpolation between two probability distributions. It was not useful at all at the beginning, but then we performed some procedure called flow matching, which allowed to construct an ordinary differential equation. Here, the logic is quite similar. So we first construct some process which interpolates between two given distributions, P0 and P1. Yes, but then we somehow construct a stochastic differential equation based on this process. So this process is not useful for generative modeling at all because in general, it is not a stochastic differential equation process. It's not a Markovian process which can be represented as a stochastic differential equation because of this non-tricky form. So because like to sample it, we need to know both start and end points. Yeah, but on the next slide, we will discuss how this process can be turned into something useful for domain translation problem, just like in flow matching. We constructed an ordinary differential equation to learn such a process. And the thing which we are going to discuss is completely analogous to what we have in flow matching, but more complex because we work with stochastic stuff now, yes. And previously we had flow matching procedure, which allowed us to turn this interpolation between two probability distribution to some ordinary differential equation. Yeah. Now we talk about the same stuff, but for stochastic differential equation. So this mathematical machinery, which allows to transform reciprocal process to a process which is represented by a stochastic differential equation and is useful for generative modeling. In short, we can write down a particular process which is called M, or Markovian projection. Why Markovian? Because it is a diffusion process, it is a Markovian process because of it, which satisfies many nice properties. So if you recall the previous lecture on flow matching, yeah, there for that interpolation between two probability distribution, we wrote with drift available in specific form, and we said that okay, this is an ordinary differential equation which interpolates between two probability distributions and satisfies a nice property that is like the tube of probability distributions over which it goes. It is the same tube as it was in our interpolation which you previously constructed. So the logic here is exactly the same. So reciprocal process is some process constructed in the between two probability distributions constructed in the following way. So we take some pairs, and into these pairs we input our reciprocal, our bridge process, our kind of interpolation between 2 points. But in this case, it's just stochastic, not deterministic. Yes, and then we turn this process into a particular process which is described by a stochastic differential equation. And this process is Markovian, and this process satisfies the property that all the marginal distributions of this process are the same as the marginal distributions in the original reciprocal process which we use to construct this process. And this process, which is called Markovian projection, it can be described as a stochastic differential equation of the following form, where this V with arrow is a drift. And this drift can be, well, in fact, computed if we know these transition probabilities of our reference initial process Q, which we use to construct our reciprocal process and our bridges, and samples from this reciprocal process. So in fact, this is something which is analogous to that theorem about slow matching, which I showed you on the previous lecture, but a little bit more complex in the sense that it's just for stochastic differential equation. It is for stochastic interpolance between points. So previously we considered just linear interpolation between points, which was deterministic and which was much simpler. And this is an explanation of it in the general form. So the question, okay, this is some stochastic process which allows to perform transfer from one distribution to the other. The question is, can we compute this drift analytically? Yes, or somehow. So can we immediately use this stochastic differential equation to perform translation of data from one domain to the other? And the answer here is the same as in flow matching. The answer is no, because to estimate this drift, yes, we need to sample some particular points from our R, which is this reciprocal process. And here we need to sample endpoint of our reciprocal process given some intermediate point. And the story here is just like in flow matching. In flow matching, to estimate this drift, which appeared in this as a result, we had to sample endpoints of our interpolation, given the intermediate points of our interpolation. And we were not able to do this for many, many reasons, because the construction of our interpolation was kind of reversed. So we first had to sample endpoints and then to sample the intermediate point given the endpoints. So here the story is the same. We cannot directly use this stochastic process, this Markovian projection for data transfer because it's unavailable, it's intractable. But one important aspect is that just like in flow matching, this unknown drift, it can be recovered by solving a certain regression problem, which is a little bit more complex than in flow matching, but there is a completely the same analogy. We'll discuss it in 2 slides. But before discussing this, I would like to mention one more a little bit tricky aspect about all this stuff. So first of all, you see that when we talked about flow matching, what we had some procedure which recovers some drift. And this drift allows to transform one probability distribution to the other probability distribution. In flow matching, since everything is based on ordinary differential equations, this drift can be immediately used to perform the reverse translation from from P1 to P0. Yeah, because it was sufficient just to take minus drift and just go backward direction. In the case of stochastic differential equations, the situation is a little bit more complex. If you have forward stochastic differential equation, then it is not that easy to write down a stochastic differential equation, backward stochastic differential equation, which where the time flows back from t capital to 0, and you do translation from second domain to the forward domain for the input domain. Actually, to recover the reverse stochastic differential equation, yeah, you can also do it by just do the same Markovian projection, but in reverse time. Well, you may ask me, why do I recall this? Why do I actually tell you about this? Why, if we can do forward and you have already given like some formulas, why do you need to consider backward stuff? Well, there are 2 reasons. First, backward stuff is more closely related to diffusion models, to diffusion models. And in fact, in the scientific papers, if you'd like to, at some point, you would like to decide, if you decide just to read some papers to understand this stuff, how it works in the more complex sense, yes, you'll find out that there are like 2 streams of papers. In one paper, they write everything in forward time. In other papers, they write in backward time. Essentially, this is the same stuff, absolutely the same, but using different terminology. So this is why it is important to understand how these concepts are related. So the short story from this slide is you can write down your Markovian projection stochastic differential equation for this in backward time. It will be the same random process, but just different formula because it's a stochastic differential equation in backward time. That's it. And so Again, let's take a look at these images. Let's just conclude what all this Markovian projection does. It takes as input some reciprocal process and in the end returns a stochastic differential equation, in this case backward in time, so that by using this stochastic differential equation you can take input points from the target domain and translate them by following these trajectories backward in time to the forward domain, and for each point x t in the target domain you can generate multiple points from input domain which correspond to this point. Okay, so now let's come to the main question. So basically, on the previous slide, I told you that, okay, you can get this stochastic differential equation, this Markovian projection, which allows to construct a stochastic differential equation. But as I already told you, it was intractable because you were not able to estimate the drift of that Markovian projection easily, just like in flow matching. But fortunately, one may design optimization loss, just like in flow matching, which allows to recover this unknown drift function of the Markovian projection. And this loss, it differs for the forward and for the reverse Markovian projection because it recovers the same process but in just different time. But it can be expressed in the following form. For example, let's take a look at the loss of the forward Markovian projections. Basically, in the forward Markovian projection, we need to recover this unknown forward drift, which is intractable because we cannot sample from endpoints given intermediate points. But this loss can be recovered as a solution to the following optimization problem. So basically, what we do in this optimization problem? In this optimization problem, there is some analogy with flow matching, and I will talk about it in a few slides in a more simpler case. But the main idea is you sample from your interpolation process, from your reciprocal process. You sample jointly endpoint and intermediate point. You can do this because you can first sample input point, endpoint, and intermediate point together. And then you regress your drift on some average, this score function, which is tractable and which is known. And there is some analogy with flow matching because with flow matching, this will be just the linear interpolation x1 minus x0. We will see this in several slides, how this very weird, very complex formula translates to simple flow matching in the particular case of this process queue. Okay, but in general, the main idea is that you kind of do the same stuff in this flow matching. You try to regress your drift function onto some average direction, but in actually it will be some average score function of many different various processes from which the current intermediate point comes from. And this problem is tractable. In practice, it can be solved with neural networks. How? So you just sample from your reciprocal process. So you sample input point, you sample endpoint, you sample from your bridge process, this point xt, and just write down your favorite L2 regression loss and optimize your network the same way. The question is, what is this monster, right? How to compute it? What is it? What is our target for regression, which we do need to use here? So basically, this is a very complex stuff because many different prior processes Q are used nowadays in the scientific literature for all these bridge matching methods. First of all, and this is closely related to the standard prior noising processes, which are used in diffusion models, not in the diffusion bridge models. And this is very closely related. So there are many examples of which prior processes can be considered for the bridge matching. The simplest and the most intuitive ever example, which in some limit case just boils to flow matching, I will talk about it in the few slides, is the Wiener process. So basically, when we take as our prior process with which we do bridge matching, just the Brownian motion, the Wiener process. In the diffusion terminology, this process is usually known as the variance exploding stochastic differential equation. Why it's variance exploding? Well, obviously because it just adds random noise to your current point, yes, and the variance obviously explodes. For this process, it is of course probably the most well-studied stochastic process ever. For this process, everything is known analytically. So it's bridge process, which is needed for bridge matching, for Markovian projection, is known analytically. So it can be written in this way. Its transition probabilities are known analytically. These are some normal distributions with particular coefficients. The same holds for the reverse time stochastic bridge associated with this Wiener process. And the bridge distribution, basically how to sample intermediate point given the endpoints, is of course also analytically known. So all this stuff needed for bridge matching. So basically how to sample from this expectation and how to compute this is known. There are some closed formulas which you can just use in your practice. The same holds for more complex stuff. So first of all, working with these diffusion models, diffusion bridges, and so on, people noted that in some cases, using Wiener process as a diffusion process, as a prior process, is not the optimal case. Sometimes if you modify some slightly its parameters and obtain some different processes, the performance in practice of such models is much better. One of the ideas, which is borrowed from standard diffusion models, is the scheduling. So basically, one process which is also widely considered is the scheduled diffusion process. What is this scheduled Wiener process? Scheduled Wiener process is basically when you add some noise to your data, but you add it not with some uniform schedule, basically like some noise of amount 1 per given time moment, but you add a different amount of noise during different time moments. For example, you can add a lot of noise at the beginning, in the middle just add not a lot of noise, and in the end add much bigger amount of noise, or vice versa. You can add a lot of noise in the middle of your time from 0 to 1 and so on. There are many different variants. Such diffusion process is described by the stochastic differential equation of this kind, where beta is a parameter, schedule parameter. And there are many different ways how this beta is typically chosen in practice. Well, take a look at these papers, for example. But in fact, for such process, everything else is also tractable analytically. You can know all this stuff which is needed to learn your drift function. Just it's analytically available, how to sample, and so on and so forth. And the most general case, which generalizes these two previous cases, is kind of the general linear stochastic differential equation. Yeah, when your drift, when some drift function also appears and some noise, and they have some particular dependence on many different parameters. This comes from standard diffusion models. Well, I will not stop on this for a long time because, well, it's just very technical stuff. The only thing which you need to know from this is if you really want, you can compute all what you need to train your bridge model. Okay, so let's basically talk about how these models actually work in practice. So a short story is they work quite well. Such diffusion bridge models, yeah. Microphone for this guy, please.
This one. Could you please explain? Am I right that's main distinction between score matching and bridge matching? is conditioning on endpoints. When score matching, we just condition on previous points.
Yes, exactly.
Thanks.
So, okay, in fact, how this stuff works in practice? This stuff works in practice really well. It works much better than conditional diffusion models because in this case, the generation of new image, the diffusion process starts not from random noise. It already starts from some meaningful object. For example, in the problem of super resolution, well, like this, well, maybe this, okay, let's take a look at deblurring. It's visually better. Yeah, the generation starts not from a random noise. It starts directly from this point. And diffusion goes from this point to some particular output point. And this is one of the reasons why this stuff outperforms diffusion models in image-to-image problems. And it also qualitatively outperforms, for example, GANs, which are also widely used in image-to-image translation problems. But just like diffusion models, there are certain problems with this stuff that, unfortunately, just like standard diffusion models, the generation of new image is still quite complex because it requires simulating a stochastic differential equation. Well, usually it requires less amount of steps in diffusion models, but it's still a pretty large amount depending on particular setup and so on and so forth. Okay, but one important aspect which you probably missed when I was talking about. So you see that this approach as input, it takes what it takes? It takes some input coupling, so basically some pairs of data, right? And builds a reciprocal process and then does the bridge matching or the Markovian projection and reconstructs some stochastic differential equation which allows to generate data of one domain from the data from other domain. But what we know about this Markovian projection? Well, we know that this stochastic differential equation which you constructed, that it transforms data from input distribution to the target distribution. But we really never know what happens with the initial coupling which we use to construct this bridge matching. Yeah, because you see that in all this previous slide, I never told what really happens with this coupling. Whether our model, which we constructed, let's call it like Markovian projection PM, which is a new joint distribution of this stochastic differential equation which constructed, whether it actually preserved the coupling. So for example, in super resolution problem, yeah, our input coupling, what is that? For example, low resolution cat, high resolution cat, low resolution dog, high resolution dog. So we applied bridge matching. And why are we sure that when we apply this new stochastic differential equation, our coupling is preserved? Why are we sure that our stochastic differential equation will not generate, for example, from this cat, this dog, and from this dog, this cat? The short answer is we never know, because bridge matching in general alters the coupling on which it is trained. So theoretically, it is possible that you train your bridge matching model on the coupling, which, for example, inputs like cat, 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 dog, but in the end, cat, cat, dog, dog, but in the end, you obtain like cat, dog, dog, cat. Yeah. You may ask why then it works here? Yeah. Why then it works here? You see that like this dog does not transform to like leopard or whatever. We'll talk about this in a more detail. But before this, we will talk about particular case of bridge matching, conditional bridge matching, which is guaranteed to preserve the coupling. And bridge matching is conditional bridge matching is the stuff which is widely used in paired supervised learning problems when you have some coupling of data and you need to preserve. But before that, let's discuss about one very important moment. How all this magic is related to flow matching. Yeah, because I told you that all this basically just generalizes flow matching. How it generalizes. Let's do the following. Let's consider as a prior process the Wiener process. Wiener process with some given variance. So basically, it is described by this stochastic differential equation. dxt equals to square root of subvariance multiplied by differential of stochastic Wiener process, of Wiener process, standard Wiener process. Basically, if we write down the bridge matching objective with the Wiener prior with given variance epsilon, yeah, so since everything is tractable here, one may note that we'll have to optimize the following loss. So basically, we'll have to regress our drift of our stochastic differential equation to this thing, which is analytically tractable thing for the Wiener process. It is just the transitional distribution of the Wiener bridge or of the Brownian bridge. Yes, and to optimize this stuff, we need to sample points with, for example, if we consider like independent plan, yes, we'll need to sample first. We sample point from input distribution, then we sample point from the target distribution, and then we sample from the bridge. And bridge looks like a normal distribution, which is centered in the same point as our interpolant is centered for flow matching, but with some variance. And if we consider this limit of this loss of this objective when our variance of our prior Wiener process converges to 0, then this stuff, stuff will actually be the stuff with 0 and x1. Yes, and this stuff will boil down to the standard objective which we have in flow matching. So roughly speaking, standard flow matching is a limiting case of bridge matching with the Wiener prior when the variance of this Wiener prior distribution converges to 0. Yeah, because the bridge from which we'll have to sample will degenerate just to like one line. Yes, it will have 0 variance. And the target for our regression on which we'll have to regress will boil down to basically x1 minus xt divided to 1 minus t. But if all these 3 points lie on the same line, then it will be just x1 minus x0. It's a small, simple exercise just to check that this whole. So that's it. Basically, bridge matching is just an extension of flow matching to more complex stochastic differential equation stuff. This is the bridge matching for the Wiener prior, yes, which returns the stochastic differential equation. This is the flow matching for the standard deterministic interpolant. You see the objectives, they are very, very simple and similar in the end. Yes, and if here you boil down to variance of your bridge distribution to 0, then in the limit you'll obtain this objective, which is flow matching. Okay, let's now talk about conditional stuff. So basically about let's talk about this problem that when you train a bridge matching on some coupling, this coupling is basically altered and it changes, which may be problematic in some domain transfer problems. Yeah, because you do not want like your cat to transform to some dog, for example, right? So, okay, what is this conditional bridge matching? So basically, let's recall this, what is unconditional bridge matching. So let's talk about this projection in the forward time just for simplicity, because, well, you can also do it in backward time. But to begin with, let's talk about forward time. So basically, if you have unconditional bridge matching, what it learns? It learns the diffusion between two distributions. It takes as input some coupling, yes, and alters the new diffusion, which may alter this coupling, by the way. So if your initial coupling was of this kind, when you do bridge matching, you may obtain something which is different. The main idea of conditional bridge matching, just the same as the idea of conditional diffusion models. So instead of learning one stochastic differential equation which transforms one distribution to the other, for each input point, let's learn a separate stochastic differential equation which will map this particular point x0 to the conditional distribution of this input points. So to the points in the target distribution which correspond to this point. What does this mean? This means that now we learn not just one model V of XTT, but we learn many models. For each x0, for each input point, we learn its own new stochastic differential equation, which does the Markovian projection of this particular process associated with just this input point. So kind of, it's not like one Markovian projection for everything which we had here, but it's many different Markovian projections conditioned on each particular input point. So how this is done in practice? In practice, we just optimize our loss the same way as in unconditional case, but with inserting additional parameter to argument to our diffusion bridge model, its drift. In this case, what we do, for each x0, we learn a diffusion which transforms point x0 to conditional distribution which corresponds to this point. So basically, if we want to visualize this, what we have, previously we just learned one stochastic differential equation. Now for each point, we have its own separate stochastic differential equation. And since it is by design trained to map this delta distribution started at this point to its conditional distribution, the coupling will be preserved. So it will be a separate diffusion which transforms just one point to its corresponding conditional distribution. And for the same will be for the other point. It will just map this point by its own separate conditioned stochastic drift, stochastic differential equation to this distribution corresponding to this point. It's a very kind of naive idea, which is the same, ideologically the same what we do in conditional diffusion models. So, right, instead of just learning one unconditional diffusion, we learn many conditional diffusions. Each diffusion starts at its corresponding point and maps its corresponding point to distribution which corresponds to this point. Yes. Right.
Am I right that for each point in P0 we learn its own equation?
Exactly.
And
Yep.
does it mean that we learn like discrete equations and finite amount of it?
No, of course, in practice, we learn not, well, in practice, we have a finite trained data set, of course, but in our neural network, we just add additional input and that's it. So the difference is that like V is usually approximated with a neural network and now it has one more input. Of course, we train on like finite data set, but it can generalize later.
So we can sample.
Yeah. Okay. So the training procedure is basically almost the same, except the fact that you just add conditions here. That's it. You can consider this as a hyperparameter to some extent. So whether you learn conditional bridge model or unconditional, but in conditional, it is guaranteed that you will preserve the coupling. One more important difference with unconditional model. So in unconditional model, you can consider bridge matching in forward time, you can consider bridge matching in reverse time, and it will be the same diffusion, just in different time. In conditional bridge matching, the situation is drastically different. First of all, in conditional bridge matching, let's consider you learn forward diffusion, yeah? you learn diffusions which are conditioned on input points. And you just cannot apply this diffusion to map your write points to end points, so backward time, because you have an input, a condition, which should be from the first domain. So you cannot use your conditional model to do both translations because by construction. For this, you can consider learning a separate conditional model in reverse time. So do conditional bridge matching in reverse time. So roughly speaking, learn a family of diffusions in backward time, which are conditioned on samples from the target domain. And this will be an absolutely separate stuff from forward time because these are different diffusions. Yes, here when you learn in forward time, your diffusions are conditioned on input point. Yeah, here you learn diffusions which are conditioned on endpoint. So while in unconditional case, forward and reverse Markovian projections are essentially the same process, just in forward and backward time. Here, these are two families of processes which are different. One family is the family of processes in forward, family of reverse diffusions conditioned on samples from the target domain. Question?
Yes. So in real data sets, we have just pairs of elements, and our distributions boils down to delta functions. So variety and why it still works if we have no distribution, we have just one sample.
Yeah, you mean so in most cases for like each x0 we have just x1. One
Yes,
x1.
so why it just doesn't normalizing flows, classical normalizing flows?
Well, it's a very interesting question, like why it generalizes, yeah, to some extent. Yeah, so I don't know.
Okay.
It just works. I mean, it looks like it's sufficient sometimes to have just one point from the target from the conditional target distribution to generalize. But another aspect is, in many cases, it suffers actually from kind of mode collapse. So when it degenerates to actually just one point. So I mean, it's a problem. It's a problem which sometimes appears, but sometimes not. What? Yes, yes, exactly. Like collapsing conditional guns. Here it also happens sometimes. Yes. So it is a problem indeed, but not always, depending on the case. Okay, so it works. I mean, these are some paired image-to-image translation problems, and there are two main papers related to these conditional diffusion bridges. One is from NVIDIA, second is from some other guys. So in a paper from NVIDIA, they consider this conditional bridge matching in forward time, so forward conditional Markov projection. In denoising diffusion bridge model, diffusion bridge matching conditional. Yes, and they apply to different problems like some colorization and so on. And to some extent, it actually works. That's it. Okay. Okay, so the final part of the lecture will be devoted to, okay, we have discussed the paired setting. Yeah, so paired setting, how diffusion bridge models work in paired setting. The question is, can these diffusion bridge models be generalized to work in unpaired setting? Yeah. The problem of unpaired setting compared to paired setting is that there are many possible solutions. Yeah, so here you teach your model, you give some particular pairs how input and target matching should look like. Here you do not have any pair. So in principle, theoretically, yeah, your model may learn some weird translations from one domain to the other like this. Yeah, because like this is a valid domain translation theoretically because it transforms one distribution to the other, but this translation is just bad in practice because it's absolutely useless for any type of application. Yeah. So in practice, when one usually talks about unpaired domain translation problems, one usually says that the model should learn certain domain translations which are reasonable from the practical perspective. And the practical perspective, such domain translation are usually associated with domain translation maps, which keep the content of the image. So there is a so-called notion of the content preservation or content similarity, which is widely propagated in this unpaired learning generative modeling subfield, which basically says that, well, your model should learn reasonable translation maps, which do not change the content of the image too much. Otherwise, it's just quite useless in practice. The question is, how can we apply bridge matching to do this, to solve the unpaired translation problem? First of all, conditional bridge matching models. Can they be applied? Well, no, as we already discussed, because in conditional bridge matching, you need to have pairs. Yeah, here in unpaired setting, you do not have pairs. Yeah, so you cannot apply condition model, unfortunately. Secondly, unconditional models. Can they be applied? Well, unconditional models, they actually also require some pairing to be trained, right? Well, you can take some independent pairing or something like that, but you never know which pairing in the end your model will learn. Yeah, but whether this pairing will be sufficiently good in the sense that if it will provide the content preservation during translation from one domain to the other. But unconditional bridge matching can be modified the same way that flow matching is modified, and to produce a rectified flow-like algorithm, which allows to recover one specific pairing of data, which in some sense preserves the content during translation from one domain to the other in the best way. And this is how it is done. So basically, recall that we previously had flow matching, and then we designed a rectified flow algorithm, which what it does, iterative. Here we can do exactly the same stuff. So we can train a bridge model by optimizing these flows, for example, starting from some independent transport plan between two, independent coupling between two probability distributions. Then, as a result of our model training, what we obtain? We obtain a stochastic differential equation, which represents a forward Markovian projection. This stochastic differential equation allows us to do what? It allows us to take an input point and generate some points in the second domain which correspond to this input point according to this stochastic differential equation. Well, what is this correspondence? We do not exactly know how it behaves, but this means that we started from independent coupling, and now can we define some other coupling of probability distributions, which is defined by our trained bridge matching model. Yeah, but unlike flow matching, this coupling will be not deterministic, because in flow matching, for one point we get just 1 point in the target domain. Here, for 1 point, we can get many points. Yeah, so it's stochastic. But anyway, this coupling, we can sample from this coupling by simulating this stochastic differential equation, and we can use this coupling again to train the new bridge matching model on top of this coupling. So basically what we do on the next step, like in rectified flows, we train a new bridge matching models, but then we sample our points x1, xt, not independently, but dependently according to our previously trained unconditional bridge matching model. So what we have, we just optimize this loss, train a new bridge matching model. That's it. And then we repeat this procedure until convergence. Okay, why do I say until convergence? Why actually some convergence happens? Where this model converges? Well, can we say something about the diffusion or like this result of convergence? Where actually there is a very nice and quite novel theory about all these Markovian projections and the iterative bridge matching, which says that this procedure converges to a particular diffusion process between two distributions, P0 and P1, which satisfies certain nice properties which may be used for unpaired domain translation. So basically, informally, very informally. Yeah, okay. This diffusion converges to a particular diffusion process, which is called the Schrödinger bridge, or in other terminology, it's called entropic optimal transport, whose coupling of this diffusion is a solution to a specific optimization problem. So basically, this coupling, which is recovered in the after the convergence of this, is the coupling between two probability distributions P0 and P1. So it's translation from one domain to the other, which minimizes some particular criterion. What is this criterion? So basically, this criterion is a little bit tricky to interpret in this way because it has some conditional distribution of your prior process. What is that? What does it mean? This is the entropy term. But let's go to a particular case. A particular case when our prior distribution is the winner process. So the simplest case of bridge matching. In this case, it is known that this solution to which this optimization procedure converges is the so-called solution of entropic optimal transport with the quadratic cost. So basically, it finds the transport of distribution P0 to distribution P1, which is the best in the sense of preservation of the content of the data when this content is measured by L2 difference between input point and the end point, plus some like entropy term, entropy regularization. I will not stop on this too much, but the main idea is up to some details, this iterative procedure, it learns a particular transformation of one distribution to the other in which the similarity of input point and in the end point is the maximal in a certain sense. And here, this is an example. So this is an example of how this procedure works on two example when you need to transform your Gaussian distribution to the Swiss roll distribution. So you take your initial coupling from which you start. It is just a reciprocal independent process. So independent product of Gaussian distribution and Swiss roll distribution, and these are just some trajectories. So you see, this is something very chaotic, yes? But when you do this procedure several times, you see that you obtain quite a nice diffusion in which when you map points from green distribution to Swiss roll, then it maps points to kind of neighbor points in your target distribution. So this coupling turns to be an optimal coupling with respect to certain entropic optimal transport optimization objective. And this coupling is quite useful in many unpaired domain translation problems. For example, when you do unpaired like super resolution of particular data related to physics, you can take a look in this paper. Or if you do some model problems like translation between different domains, for example, between the domain of like cats, wild animals and cats, yes, you do not have pairs here. Yeah, you cannot easily get a pair of cat and corresponding dog or corresponding wild animal to it. Yes, you cannot find easily such pair on the internet. So you have to train such models in unpaired setting. And yes, in this case, it allows to learn a mapping which preserves the similarity between input and output point. Yes, so this like wolf or what is that is mapped to like white cat, not just to like orange cat or whatever. Yes, so this is the property of this iterative diffusion matching procedure, that it finds a diffusion which maximally preserves the input content in the unpaired setting. Okay, of course, this procedure, just like rectified flows, has its own limitations. The limitations are exactly the same as in rectified flows. So basically, if you do this procedure, there are two limitations. First, to train this procedure on the next steps after the first, you have to do simulations of your diffusion learned from the previous step. This is one limitation. Second limitation is the error accumulation, just in rectified flows. But unlike rectified flows, this procedure has a kind of theoretical extension, which is called bidirectional iterative Markovian fitting or bidirectional iterative diffusion bridge matching, which actually solves all these problems and does not accumulate error, unlike rectified flows. So in case of diffusion bridges, unlike rectified flows, you can do this procedure in practice, like for any time horizon, you will not accumulate the error, but you need to do certain modifications. I will not discuss them during the lecture. If you're interested, take a look at these 2 points, 2 papers. Okay, and finally, there are some extensions. I'll very briefly talk about, just tell about them. In fact, me and my group, we work in this direction a lot. So, and we have some papers related to this. For example, well, if we talk about diffusion bridges, if you want to obtain this Schrödinger bridge, this solution of entropic transport, there is no need to do iterative learning. You can do it in just one bridge matching step, but some optimal in some sense. If you're interested, take a look at this paper. Secondly, you can do the same for flow matching. If you want to obtain a model with straight trajectories in flow matching, well, you do not need to repeat rectified flows. You can do kind of optimal flow matching just once. Thirdly, one of the limitations of all these bridge matching models is they are computationally time consuming at inference because you have to sample from your diffusion process. You can actually avoid this by considering diffusion bridges in discrete time and using adversarial framework to learn your model. So if you're interested, take a look here. And finally, this stuff can be applied to discrete diffusions as well. So we have a paper related to this called categorical Schrödinger bridge matching. All these diffusion bridge models, they provide a very good quality, but they are very slow because they anyway need to simulate diffusion process. But you can distill them. You can distill them quite using quite nice mathematical framework of inverse optimization, and actually also know how to do it. Let's take a look here. And so to conclude, so is a quite complex extension of flow matching. It's related to diffusion models as well. It can be used in conditional manner, in unconditional manner. It can be applied to paired, supervised or unsupervised learning problems in many different ways. Yes, so that's it. Any questions?
Раз. Oh. Okay, thank you very much for your lectures. My question is, so we all know that diffusion scales pretty good in production. Are here any scaling laws in bridge matching and in normalizing flows? Does this framework scale on datasets of billions of?
Essentially, the answer is yes, because essentially this framework on more condition. Yeah. As for in scientific literature, since this stuff is usually applied to some domain translation problems like super resolution and so on, yes, so the examples which are considered there are not, I would say, that big as in text-to-image diffusion models. Like they do not generate like 124 by 124 images, whatever. Since such stuff is usually considered for super resolution and so on, it's sufficient to train at small scales like 256 by 256 and so on. And all this stuff, it really works well. For example, this paper by NVIDIA, which is like image-to-image Schrödinger bridge, is the paper from NVIDIA. Well, they trained some good models for super resolution on ImageNet at some, well, I don't remember the scale. It's like 256 by 256, but it's very computationally extensive. So this is a problem. Training is, even on this ImageNet, requires like 8 A100 GPUs and 2 weeks of training.
Okay, so I'm talking about scaling in terms of dataset size, not image size.
Okay.
So, are
Well,
there any comparisons between diffusion and bridge matching in terms of computation? What is heavier? What is?
I would say no. I haven't seen such comparisons between diffusion and bridge matching, but at least in my practice, they really require a lot of data to work, just like diffusion models. But how many? I don't know.
Okay, thank you. Thank you very much.
Yeah, thank you for the lecture. I have some more practical question. In domain translation problems, your data should have same dimensionality, right?
Yes. Yes.
And in case of images, you can like apply some interpolations, and it's pretty straightforward how to do. But what if data is more complex, like vectors or some other stuff? What?
Most of these domain translation problems are usually formulated the way that your data is the same, by definition. Yes, in super resolution, maybe the scale is not the same, but yes, you can upscale and so on. Yes, as this stuff is not applicable if you want to do, for example, like text to image, because you cannot start your diffusion from text and then on image. This is
Well, it is from categorical to from discrete to
yes. So the space on which your diffusion goes should be of the same dimension.
Yeah, so it's kind of my problem to prepare the data such that it's same dimensionality, right?
If it's same, you can easily apply.
Yeah. Okay. Thank you.
Thank you for your lecture. This whole thing with unpaired data set looks a little bit like calibration. So is there something like you can add a small set of paired data on top of unpaired data so that it calibrates and makes the problem more simple?
Well, the problem is, well, sometimes indeed you can like get a small amount of paired data, but the problem is that it is hard to design some loss function which will be able to train model both on paired and unpaired data. This is the problem. So you see, if we talk about paired data, we train conditional model, but you cannot use unpaired data in this case. Yes. If we talk about unpaired models, then well, it's unconditional usually, but how to use paired data? It's easier if we talk about GAN framework, because there you can just easily stack several losses for different GANs, conditional, unconditional, whatever. But if we talk about diffusions, then everything becomes more complicated. I would say that a particular way how to overcome this issue is to train some unconditional model and somehow combine it with like classifier or classifier-free guidance, as it is done in like text-to-image models. But this is also not so straightforward for diffusion bridge framework, because not all this stuff with like classifier guidance and some can be easily translated here.
Thank you.